Good morning, my dear students. Now we discuss Unit 2, which is three-phase induction machines. Already in previous semester, you learned about transformers and three-phase transformers, single-phase transformers and three-phase transformers. Now we learn about three-phase induction machines. So this is a Unit 2. So what is the working principle of an induction motor? The motor which works on the principle of electromagnetic induction is known as the induction motor. Electromagnetic induction is the phenomena in which the electromotive force induces across the electrical conductor when it is placed in a rotating magnetic field. Normally, the transformer working principles are also mutual induction principle. But in transformer there is no rotating part, but in induction motor there is a rotating part. The stator and rotor, two essential parts of the motor. Any rotating machine there must be a two parts, that is a stator and rotor. The stator is the stationary part and it carries the overlapping winding, while the rotor carries the main or field winding. The winding of the stator are equally displaced from each other by an angle of 120 degrees. Already we know that in any three-phase system, one phase to another phase there is an angle difference of 120 degrees. Totally the from A to C, from A to B 120, B to C 120, C to A again 120 degrees. If there is a balanced system, the induction motor is the singly excited motor. We given only one supply, that is a three-phase supply, so we will call induction motor is a singly excited motor. The supply is applied only to the one part on stator. The term excitation means the process of inducing the magnetic field on the parts of the motor. The process of inducing the magnetic field is nothing but excitation. When the three-phase supply is given to the stator, the rotating magnetic field produced on it. So please see, this is an induction motor diagram. The stator, rotor, three-phase AC supply. This is a shaft, the poles north and south. This is a three-phase induction machine. They have two parts, stator and rotor. They are having two windings, stator also one winding, the rotor also another winding. We given the supplies to stator, three-phase AC supply. Consider that the rotating magnetic field induces in the anti-clockwise direction. The conductors of the rotor are stationary. The stationary conductor cut the rotating magnetic field of the stator, and because of the electromagnetic induction, the EMF induced in the rotor. The conductors of the rotors are short circuited either by the end rings or by the help of external resistance. The relative motion between the rotating magnetic field and the rotor conductor induces the current in the rotor. Now we have two fluxes, one because of the rotor and another because of the stator. These fluxes interact with each other. On one end of the conductor, the fluxes cancel each other. On another end, the density of the flux is very high. Thus, the high density flux tries to push the conductor of the rotor towards the low density flux region. This phenomena induces the torque on the conductor, and this torque is known as electromagnetic torque. Thus, the high density flux tries to push the conductor of the rotor towards the low density flux region. This phenomena induces the torque on the conductor, and this torque is known as electromagnetic torque. The direction of electromagnetic torque and the rotating magnetic field is the same. Thus, the rotor starts rotating in the same direction as that of rotating magnetic field. The speed of the rotor is always less than the rotating magnetic field or synchronous speed. So, what is the synchronous speed? Synchronous speed ns is equal to 120 f by p. The induction motor rotates always less than the synchronous speed. If the rotor is rotated more than the synchronous speed, that is called induction generator. The rotor tries to run at the speed of the rotor, but it always slips away. So, why rotor never runs at synchronous speed? This is very important. If the speed of the rotor is equal to the synchronous speed, there is no relative motion occur between the rotating magnetic field of the stator and the conductor of the rotor. Thus, the EMF is not induced on the conductor. If the motor rotates at the speed of synchronous speed, there is no EMF induced in the conductor. If there is no EMF induced, there is no current induced in the rotor circuit. Finally, there is no torque produced in the motor, and zero current develops on it. Without current, the torque is also not produced. So, the three-phase induction motor never runs at synchronous speed. So, why we using the synchronous induction motors are very frequently? There are some advantages. One is it is cheaper in cost compared to another machines. Its construction is simple compared to another machines and robust, mechanically strong. It has more efficiency and more reliable. It requires less maintenance and has more overload capacity. Its starting torque is more compared to another motors. So these are the advantages of three-phase induction machines. So the induction motor is an AC machine which converts AC electrical energy into mechanical energy. The three-phase induction motor is commonly used AC motor for industrial or commercial application because of the following advantages. Already we discussed these advantages. The rotor or stator slot of the induction motor skewed is a very important topic through some angle, so that the bars lie under alternate harmonic poles of the same polarity or other. So these are the three-phase induction motor: stator part, this one is a rotor part, this is a bearings or end bells. Please observe carefully. So this is a three-phase induction motor diagram. Practically, please observe the parts of induction motor. This is a rotor circuit. In the rotor circuit, the bars are skewed, means that's not in straight line, that is a inclined. Why this is inclined, we discuss. Construction of three-phase induction motor. The three-phase induction motor mainly consists of two parts. One is stator, another one is rotor. Any rotating machine, there is a two parts only. There is a stator, another one is rotor. Stator is stationary part. It is made up of high grade steel lamination to reduce eddy current losses. The laminations are insulated from each other and slots are provided as shown in figure 1 to place the three-phase stator winding in the stator slots. Please observe carefully. This is a stator core, stator winding, stator slots. The stator winding is made of copper material and the stator winding may be star or delta connection. Here the stator poles are created by providing the stator slots. when the 3-phase AC supply is given to the stator, a 3-phase alternating flux set up in the stator core, and the stator flux is running with synchronous speed along with stator core. What is the synchronous speed? Synchronous speed NS is equal to 120 F by P, where NS is the synchronous speed, F is a frequency. In India, frequency is equal to 50 Hz, P is a number of poles. That means the synchronous speed is depends upon the number of poles. If the number of poles are increases, definitely the synchronous speed is decreases. Rotor. Rotor is a rotating part. The rotor is in cylindrical shape and is laminated to reduce the eddy current losses. The rotor has rotor slots to house the rotor winding. Constructionally, the rotors are classified as two types. Those are squirrel cage rotor, face wound or slip-ring rotor. So please see the rotor circuit. This is a skewed slots. There is a inclined. Short circuit rings. This is a bearings. This is a rotor shaft. Please observe the rotor bars slightly skewed. Already we discussed what is the skew. I discuss later. Please see the rotor bars are some inclined, not straight line. That is some inclined. This is a rotor bars slightly skewed. These are the end rings. The skewing of rotor offers the following advantages. Why we using the skewing is a very important phenomena. It reduces the magnetic locking of the stator and rotor. Magnetic locking means some north to north or south to south poles are unlike poles are attract each other, same poles are repel each other. Here magnetic locking means the rotor does not rotate in any direction. So this skewing causes that rotor reduces the magnetic locking of the stator and rotor. It reduces the humming noise during the operation. More torque produces, noise is reduces during the operation. So this is the slip ring induction motor. Slip rings. These are the slip rings. So diagrammatically, these are the slip ring 3-phase induction motor. So previous we see the squirrel gauge. So this one is a slip ring. So this is a squirrel cage type rotor. This is a squirrel cage type rotor. So this is slip ring rotors. Second type of rotors, slip ring rotors. Here we adding external resistance to the circuit. Because of adding external resistance, the rotor torque is increases initially. The starting torque is increases due to external connected rheostat or resistance. The face wound rotor is also known as slip ring rotor, and the motor having slip ring rotor is called slip ring induction motor. This type of rotor consists of 3 slip rings which are mounted on the shaft with brushes as shown in figure. The brushes are connected to star connected variable resistor. The main use of brushes and slip rings are to connect the external resistance to rotor. The use of connecting external resistance to rotor circuit is it increases the starting torque and decreases the starting current. It controls the speed of the motor. Comparison between squirrel cage and slip ring rotor. So in squirrel cage rotor, that is a simple and robust construction. Slip ring rotors are difficult in construction. It requires less maintenance because of absent brushes. It requires more maintenance. No possibility of connecting external resistance to rotor circuit because the rotor windings are short circuited. Additional resistance can be connected to rotor circuit to increase the starting torque and to reduce the starting current. Higher efficiency and higher power factor in squirrel cage rotor. Efficiency decreases due to power losses in additional resistance in rotor. Its cost is low due to absence of brushes and slip rings. Its cost is more. So the next important topic in three-phase induction motor is production of rotating magnetic field. The production of rotating magnetic field in any machine is a very important. When the three-phase AC supply is given to the stator, a rotating magnetic flux is developed and is rotating with the speed of synchronous speed. The rotating magnetic field speed is synchronous speed. Let pi m is a maximum flux, pi r, pi y, pi b are fluxes due to r by b, pace and are given by. Due to the pace r, phi r, due to the pace y, phi y, due to the pace b, phi b. Phi m is a maximum flux. So we know that every current at an angle of 120 degrees, every pace current at an angle of 120 degrees. Similar manner, every flux also the angle difference is 120 degrees. So phi r is equal to phi m sin omega t, pi y is equal to pi m sin omega t minus 120, pi b is equal to pi m sin omega t minus 240. The angle difference between any two phases, that is a flux or currents or voltage, is under balanced condition, that is a 120 degrees. Here pi r is a reference quantity. When omega t is equal to 0, so substitute omega t is equal to 0 in above equation, we get phi r is equal to 0, phi y is equal to minus root 3 by 2 pi m, pi b is equal to root 3 by 2 phi m. So construct vector diagram. We know that we have only phi y is a negative value, pi by is a positive value. We know this is a phi r, this is phi y, this is pi b. So each are at 120 degrees. If this is a phi r, what is minus pi r? Exactly opposite. If it is a pi y, what is the minus pi y? Exactly opposite. This is a pi b. So what is the minus pi b? Exactly opposite. Here we have only pi y and pi b. Pi y also negative. If there is a pi y, so minus pi y is here. This is pi b. This is a pi b. So we need to find out resultant flux in between pi b and minus pi y. So the resultant flux we find out pi b square. So here pi y is a minus pi y square minus 2 pi b minus pi y cos 60. If you solve this one, we get the resultant flux is 1.5 pi m. So take when omega t is equal to 60 degrees, we get pi r and minus pi y value. The pi b becomes 0. Here also we have only two phasors. One is phi r, another one is pi y. So here these two also find out the resultant flux. We get the same value. Whenever the omega t is equal to 120 degrees, we get phi r is equal to root 3 by 2 pi m, pi y is equal to 0, pi b is equal to minus root 3 by 2 pi m. Here we have phi r and minus pi b. If you find out the resultant flux, that's also 3 by 2 pi m. So if you take an omega t is equal to 180 degrees, here also pi y and pi b minus pi b are present, pi r is equal to 0. At any instant of time, two phasors are, there is a value, one is positive, another one is negative, another phasor is a 0 at any time. So we get the resultant flux also 1.5 pi m at any time. At the omega t is equal to 0, 60, omega t is equal to 180 or 240, whatever the angle difference, we get the resultant flux is equal to 3 by 2 pi m. That is nothing but 1.5 times of maximum flux. This way the rotor rotating magnetic field produce constant. The production of rotating magnetic field is a constant. Please observe carefully. So synchronous speed So what is synchronous speed? From the above analysis, it is clear that at any instant of time, the resultant flux is 1.5 times the maximum flux. The direction of the rotating magnetic field in the stator core is in anti-clockwise direction, and this magnetic field is rotating with speed of ns is equal to 120 f by p. So slip is a very important topic. We discussed in next class.